Hi guys, welcome back to the video on HYSYS. In the last video, we actually talked about air coolers and heat exchangers. So now we want to complete the recycle loop for this plug flow reactor, or the fixed bed reactor in fact. This should be called fixed bed reactor because it has catalyst inside. So it's a fixed bed reactor. Okay. So yeah, where we last left off, we have cooled our effluent from 70 degrees to 50 degrees using an air cooler. So now you'll be asking me probably, how do you estimate the duty of an air cooler? Well, there are a few things we should note. Firstly, how much pressure is, how much electrical duty is it using? We can use this simple calculation found here. It's just a heuristics based on fan efficiency. And now, how much energy are we using? Well, we can take a look at this pressure drop of, or pressure increase of 0.5 inches of H2O. Alright, so 0.5 inches of H2O. So that is basically 250 pascals. Not a lot, so it's about 0.25 kilopascals. And what we can use to estimate the duty is basically pretend the fan is a compressor. Okay, so I'm just going to make a compressor right now, you see on the screen. So I'll just call this the fan. Now this will of course be an overestimate of the duty, but it should give us an idea of how much energy we are using. So let's take a look. We'll have 32 degrees of air coming at 1 atmosphere, and the composition is of course 79% nitrogen, 21% oxygen. Let's press OK. There you go. So I'll just call this stream air in and the other stream air out. Now acid gas is a decent fluid package model we can use for this, so we'll just stick with that. And how much air are we actually using? Well, you can look at this in the air cooler sheet. We can look at the worksheet and we can look at the mass flow. The mass flow is about 4.5774 kg per hour. So 4.5774 times 10 to the 4. So just put E4, press enter. There you go. And how much is the energy? You can just drag out the energy stream, and we saw that 0.25 kPa is about half an inch of H2O. So we go with that. So 101.6 kPa, that's the estimate of the pressure of the air out. And we can see that the power being used is quite minuscule, about 4 to 5 kilowatts at most. So we give and take, our air cooler is going to only take about at most, maybe if you increase it like 10 times, 44 kilowatts, which is actually not a lot. Not a lot as compared to, let's say, a compressor, which is going to change the pressure by a few few tens of kPa's. And you can see why air cooling is very cheap, because there's so little energy being used. Okay, so that's a duty estimation. That's one basic, very simple way of estimating duty for our air cooler. So basically we use a compressor which we pretend is a fan. So that's pretty much it for estimating the duty for our air cooler. So it's just a very simple estimation method. Now we look at our effluent, which has basically lots of methanol, water, CO2, CO, and hydrogen. So we need to separate the liquid from the vapor. So to do that, we just go to the models and stream palette, which we can access by pressing F4. And we will click on the first, this one here, this tab called the separator. And this is basically also known as the flash drum or the knockout drum, or knockout drum, or put KO drum. So that's what it's usually called in industry. So let's take the effluent and separate the vapor from the liquid. Yeah, okay, vapor from liquid. So I put the liquid MEOH, methanol and water mixture. And of course I will put the air mixture or gas mixtures, gas effluent or gas recycle. So yeah, the gas recycle and purge will be coming out the top. So this we can send to the distillation column. This stream, the methanol and water stream, will be sent to the distillation column. And you can find that yes, there is a little bit, just a little bit of CO2 and hydrogen dissolved due to the high pressure, but that's fine, we can get that out later. More importantly though is to deal with this recycle stream that's coming at 50 degrees, and we kind of got to make up some of that unused. We got to make up, got to top up some of the carbon dioxide and hydrogen to make enough of feed for the reactor. So how much are we supposed to top up? Well, based on this stream we want about 4150 kgmole per hour of hydrogen. So let's put that in the Excel just for easy calculation. Hydrogen reactor feed 4150, and effluent is how much? Effluent will be about 3385. So let's put 3385, and makeup will be the feed less the effluent. So 765 kgmole per hour. And for the other one, the carbon dioxide, we will need about 850 minus 530. So let's do that. 850, 530, and we'll just copy the formula over. We'll find that we need about 320 kgmole per hour of carbon dioxide. So let's just do that. Maybe in fact a bit less, because there's carbon monoxide as well, which can then be converted back to carbon dioxide. So I'm just going to drag this and put a recycle on it. So I'll put this as a recycle stream. The fluid package used will be Peng Robinson. Okay. Okay, I just assume for now there's no need to purge. But the minute that there are inerts in there, you have to purge some of the recycle stream so that you don't have an inert buildup in your system. Alright, so moving on, we will have this stream 1 here, which is our recycle stream basically. So gas RCY, I'm just going to put it as that. And we find that we need 2 fresh feeds. Okay, so one is the CO2 fresh feed, which fluid package will be Peng Robinson again, and hydrogen fresh feed. Alright, so now we have we need to put in our composition. This is CO2, so I'm just going to assume most of it or all of it is going to be pure CO2, and we need to put that molar flow rate, which I will put at 320 for now. 320. And of course, since there's extra, carbon monoxide in there, we kind of, I'm skipping some steps here. There's some carbon monoxide inside there, which acts as a carbon source as well. So I'll need to add that in as well, so that I don't put too much CO2 into the system. So let's add 94 kgmole per hour of carbon monoxide into our equation here. So I'll just take 320 minus 94 or 95. I just round it up. So 225 is all that's needed. Let's put 225. 225 just over here. Alright. and that will give you the CO2 fresh feed. For hydrogen, we'll need 765. 765. So let's put the compositions. And hydrogen. Wait, composition is already done. Hydrogen 765. So it's roughly this much, give or take. Now your next question is, what pressure and temperature do we set our fresh feed at? Well, we know that we eventually need to get it to a pressure of about 80 bar, and we know that this recycle stream will need to be, all of this needs to be heated up to about 244 or 250 degrees C. So no problem there. And we'll need to pressurize this recycle stream from 7805 kPa to about 80 bar. So the question is, how should we have our fresh feed and makeup feeds in this system? Well, one of the ways is that we can pre-mix everything using a mixer. So I'm just going to press F4. I'll assume this fresh feed comes in at 50 degrees C, and the pressure is about 7805 bar, 7805 kPa. Now I'll do the same for this. So temperature is 50, 7805. Okay, so I'll assume all of this goes into this mixer here. Okay, this should be Peng Robinson. So I'm going to delete that string cutter. That changes the fluid package. Okay, then I'll draw one string out. Okay, so this is the fresh feed. Okay, so I mean that's one way of doing it, and then you can feed that into the heat exchanger, and then you compress it in just before the reactor. Now what will that do? Now the thing is that when we compress hot gases, they tend to get even hotter. So I mean that's a good thing. We want heat generated at a high temperature so that we can recover it more using a high pressure steam generation. So let's just do that. Okay, I shouldn't call this fresh feed. Let's just call it reactor feed. Okay, so what I'm going to do, I will need to unconvert some of the heat exchanger back to non-rigorous models, because this recycle stream is going to need time to converge, and when it does that, the streams will, the molar flow rates will change, and the heat exchanger duty will also change. So I can't fix the area anymore, and that's not the point of it. So I'm gonna that shouldn't be the case. Yeah. So we'll change it back to simple and let it converge again. All right. So yeah. Let's just do this. Break connection here. I'll keep this one side, and I'll break this connection. Okay, save first. Break this connection here, because I will need to put a compressor there. Okay, so I'm going to drag this reactor feed in. Okay, so there's a consistency error. That's quite normal. Okay, I'm going to delete this, and I'm going to delete this. I just want a temperature of about 244, and I'm going to delete this and this, and press OK, and clear the composition data and everything else. So I'm just going to leave it out at 244. Alright, so I need to compress this all the way up to about 80 bar. Okay, there you go. Alright, so let's just get this preheat reactor feed. I'll just call it reactor feed, pressurized and heated. And the pressure should be 80, thereabout. And I need a duty stream for this compressor. So I just name it compressor duty. And how much duty is it using? At present, about 500 kilowatts. And this stream will be going in at about 255 degrees C. Yep. And let's just connect it to the reactor and let it converge. Now, you can see that HYSYS is going to run and iterate this this reactor system with recycle very slowly, because we've put it at 50 step sizes in this fixed bed reactor, and you can see that the more step sizes you put, the more calculations HYSYS will need to carry out. And if you want to reduce that, we can reduce the number of step sizes. So by reducing the number of step sizes, of course the accuracy kind of diminishes, but it brings us closer to the actual answer. So let's say if we put a step size of 10, or 10 segments, in fact 10 segments, we will get maybe 70 to 80% of the way there, but it's going to be much faster. And after we've converged the simulation the first time round, we can increase it back to 20 and then 50, so that the convergence is actually faster. So when you converge, just make sure, these are some tips that can actually help you converge it faster. So you see HYSYS is going to run this iterations faster and faster. Yep. And you can see this actually building up. Take a look. So we can see that the hydrogen inlet feed to this system is about 92%, 92 more percent, which is a little way too high compared to what we want. And you can see that the streams are, you can see the molar flow is getting larger and larger. So before you know it, there'll be too much flow to the reactor to do anything good. In fact, if there's too much flow, Egan's equation will dictate that there'll be too high a pressure drop, and basically the simulation will blow up. So you can see that the molar flow rate is about more than 10,000 now, and it's going to keep building up and building up. So do you want this to continue? Probably not. Probably want to stop this simulation. And what you probably want to do is to reduce the hydrogen flow rate by a lot. So let's reduce it to about, see what's this CO2 fresh feed. It's 225. So stoichiometrically speaking, we need about 3 times the moles of hydrogen to the moles of CO2, because that's basically mass balance. Yeah. So 225, let's multiply by 3 and see how much we should actually be putting in. So 675 kg per hour of hydrogen. So it's not just about making up the feed, you got to consider the stoichiometric ratio of the reactants as well. So let's reduce this to 675. So the thing is that while the simulation is converging, you got to take a look at all the molar flows. And look at this. Now it's converged. When we have stoichiometrically balanced everything, but the molar flow is pretty high. The molar flow is like more than half of what we want. So we want the molar flow of this stream to be a lot less, at about 5,000 kg mole per hour. Okay, and we want this CO2 composition to be around 17%, where according to the research paper of SCSIPAC, it will be optimal around there. So we'll need to reduce the hydrogen concentration a lot. So what we do first, we remember that we need to set our molar flow rate at about 675. That's the steady state value. So I'm just going to put it at 0 first and let it iterate a few times. So you can see this molar flow here is going to start dropping a lot. Okay, so now it's a bit too much. Now you can see that there are negative feed entering this fixed bed reactor system. So basically, yeah, there's negative feed. Nothing wrong with that. I mean, yeah, there's something wrong with that, of course. Okay, so I'm going to put this feed at 675. And let's adjust the recycle, both to 0. And let's have this stream at about 4000. That's the initial gas. And let's have it here about 3600. And why do I guess that? Basically, that's what we had before. You see this cooled reactor effluence about 4613. So I'll just have this okay, about 4613 then. I'll just use it at 4613. And the gas recycle, we'll just assume. We'll take a look at the molar flow rates here. Yeah. So it's about 4000, give or take. So 541 plus 115 plus 3453. A little over. Okay, let's see. Gas phase. kg mole 4380. 4380 kg mole per hour in the vapor phase. So let's do 4380. Or slightly less than that. 4200. So by doing that, we've provided initial gas rates for our recycle streams, and that should help it converge better. Now we are back at 5000 thereabouts. So you can see the composition. Yeah, the CO2 composition is steadily increasing. And again, we have a little too much feed. So now it's converged, but the molar flow is at about 6000 plus. So let's do the similar trick. Maybe I'll tone it down a bit. 500 kg mole per hour of hydrogen fresh feed. Okay. Now it's now it's way below 5000. 5000 kg mole per hour this reactor feed, so we'll increase it back to 675. Hopefully it will give us the steady state of about 5000 kg mole per hour, or just slightly above. And now it's back at 4939 kg mole per hour. So we have converged our first stream. Well, we have done convergence of our first reactor system, or not. Well, look at this hand RCY. This recycle operator needs to have a few more iterations before it actually converges. So let's just press the continue button. So we're going to continue converging it. And if we need more iterations, we just go to the parameters. Okay, hold on here. We look at the parameters tab. So that's the second from the left. We go to the convergence parameters. We look at the maximum iterations. We can increase it from 10 to 100, so that, you know, while this recycle streams are working, we can just like go to the toilet or have coffee or something like that. So it will just let it converge for the time being. All right. So let's see what's going on. It's going back to about 17% of CO2. That's good news, because the thing is stabilizing. So we'll need to keep watching. We'll need to keep watching what the streams are doing as it's stabilizing. Okay, give it a little longer. Hopefully it starts to converge. Well, if you want to do it even faster, we can just reduce the number of segments down to 5. So I'm just going to do that so that we can just quickly wrap this tutorial up. Should help it converge a lot faster. We are at 50-50 now. It seems that not enough CO2 is being converted, but just let it converge first. Then we'll swap it to 10 later. And reach a new steady state value. As you can see, this recycle operations are pretty time consuming. So yeah, we should, if you want to converge it faster, you got to find as many kinds of tips and tricks to tweak your simulation while it is converging, so that we can reach the convergence point a lot faster. So now you can see the CO2 stream is like going down a lot. The composition of CO2 is falling, and based on looking at the mole flows, you can see that CO2 is again being consumed while hydrogen is increasing. And it should be reaching steady state hopefully soon. Hmm. 674, 622. So, what do you think we can do to get it faster? You can see if the CO2 count is actually decreasing. We can skip a few iteration steps. Okay. So CO2 out's about 430. And in this gas recycle, it's also about 430. If this is decreasing, so we can skip a few steps. So instead of it being at 429, we can decrease it down to 350 for both. At each recycle stream, we need to change the composition. So that will give it different initial gases. So for every recycle stream, you should be doing that. And you just press active. So yeah, now it's converged very quickly, thankfully. So you see the maximum temperature is about 278.9. No problem. Yeah, I think I'll probably stop the video here. It's about 30 minutes already. So in the next video, we want to start tweaking our system and sorting out any of the possible errors that could have arisen during our process of converging. So thanks for watching. I'll see you guys in the next video. Bye bye.